Hello, my name is Major Derek Worth, and for my final project I explored the use of relative pose estimation using multi-object detection and perspective endpoint. To illustrate what I mean by this, consider a simple mailbox analogy. For most of us, placing a letter in the mailbox is a trivial task. But what if your senses were limited to a video feed from a camera attached to your head? If you knew the camera's orientation relative to your body, you could use that feed to center the mailbox in your field of view and simply toss the letter forward. Now consider what happens if your camera is bumped and you no longer have its exact orientation relative to your body. You could use the same method, but you won't get the same results. Another approach, which I use in this project, involves relative pose information about multiple objects in the same image frame. Here, even with a distorted view, we can easily use image information to move into a position that guarantees delivery of the letter into the mailbox. For my project, instead of detecting a mailbox and letter in the image frame, I detect a receiver aircraft and refueling drogue, and instead of guiding the letter into the mailbox, I send relative pose information to an autopilot on board the aircraft so it can guide its refueling probe to the drogue. In order to simulate this environment, I extended the Solve PMP project from class by installing a probe on the side of the aircraft, imported an existing drogue basket model, and created the drogue hose from index geometry. The hose is composed of 50 rings, each with 16 vertices fit evenly spaced along a parabolic curve to closely model the sweeping curve you see in actual refueling operations. For feature detection, I used a similar method to what we used in the Solve PMP project, where points are detected along the HSV color spectrum. However, instead of one point cloud, I used two, one for the receiver and one for the drogue. The scenario here represents a typical aerial refueling mission in which a buddy pod attached to the wing of a tanker aircraft can cast out its drogue basket and allow the receiver aircraft to dock and receive fuel. So I set the hose feed point next to the camera mounted on the wing, which doubles as a frame buffer object image sensor. In this setup, the feed point remains fixed next to the camera 1 meter in the positive Y direction, and its cast and drop of the basket always remains in the direction of airflow, defined here as the positive X direction. Outside these constraints, the other objects, including the camera, can move freely. One side objective here was a data collect for a machine learning project in another class. To meet this objective, I created a randomize function that randomly sets the cast of the drogue as well as the pose of the receiver and camera. Running Solve PMP then captures the image, detects the points for both the drogue and receiver, computes estimated relative poses, and updates the local frame tubes to visualize those estimates. For the data collect, I simply place the randomize function, Solve PMP, and a file writer in a for loop, which this button turns on and off. On my laptop, this captures approximately 100,000 observations every 8 hours. The output file looks something like this, where we see UV coordinates of the sensed pixels, actual 6 DOF information about the drogue, camera, and receiver, as well as the predicted and actual probe to drogue vectors, which I'll explain in detail in just a bit. Returning back to the simulation, one of my research questions was whether or not this relative pose multi-object detection method could safely and accurately guide the receiver to the drogue using only image data without any knowledge of the camera's extrinsics. So I implemented a simple autopilot that takes in probe to drogue vectors and flies a pattern that first aligns its probe behind the drogue, then moves forward to dock into the basket. Now, by using the randomize function, we can gain intuition on how well this method performs. It's important to note here how the probe to drogue vectors guiding the autopilot are generated. For this, let's switch over to the output sensor's view. Here, we can visualize the sensed points, both for the receiver and drogue. These sensed points are sent directly to perspective endpoint, which estimates the pose of the two objects relative to the camera's image frame. From these two pose estimates and a receiver to probe offset, one can easily compute a probe to drogue vector, still in the camera's image frame. To transform the vector to the receiver's local frame, you simply matrix multiply it by the estimated pose generated by perspective endpoint. The end result is a vector the autopilot can use to know where the drogue is in relation to its probe in the receiver's local frame, all without any knowledge of the camera's pose. As you can see, the autopilot finds its mark regardless of the camera's orientation. Even rolling the camera upside down doesn't negatively impact accurate probe-to-drogue estimates. The scrolling plots on the right show the real-time residual error between the predicted and actual probe-to-drogue vectors. As a side note, the receiver movement is partially implemented with linear interpolation and quaternions, and as part of the machine learning data collect, I've also implemented image distortion, which my machine learning model automatically corrects for without the use of checkerboards. You'll have to watch my other video to see those results. Future work and the next logical step here could include implementing this setup in a Vicon chamber with real camera images. That concludes my project. Thanks for watching.